So let's dive in. So today I'm not doing a PowerPoint. I've uploaded this example sheet as a PDF to the classroom, or you can feel free to take notes on a separate piece of paper, whatever you like. This personally interests me a lot. I watch a lot of NBA basketball content. So whether it's on TV or reading magazines or listening to podcasts, around playoff time or even like starts of seasons, these kind of entertainment vehicles produce a large volume of content. Thousands of analysts, people with a lot of experience or little, making their predictions on who's going to win, not just in each individual playoff series, but who's going to win the championship overall. So we are going to do some examples. We will examine for you guys. We're going to examine some increasingly more involved questions where we analyze a playoff series. We're going to start relatively simple. We're going to start with we're going to say the Dragons and Ravens, and they're playing in a best of three game series to determine who's going to win their ball hockey league. So we can apply this to any sport we want. We're just choosing ball hockey. So a best of three, we have to be really clear. It means that when a team wins twice, the series is over. So if a team wins the first two games, they don't play a third game. So that takes some getting used to if you don't watch a lot of sports. But that's our starting point. And we're going to look at this from the Dragons' perspective. And based on league play, they have a 70% chance of winning each game. We're going to keep it simple. So to analyze their chance of winning the series, we're going to draw a tree diagram. So the tree diagram for this problem is not overly complex. Later on, we will do a tree diagram for a best of five series. So let's draw the tree diagram first. We got a lot of space here. We might not use it all. That's okay. So for game one, from the Dragons' perspective, what can happen? They could win or they can lose. And it might be a good idea, I'm going to suggest it, that underneath each you put the probability of it happening. So for winning, that's 70%, or it's a decimal 0.7. And for losing, that means they have a 0.3 chance as a decimal, 30% chance of losing. That's what could happen for game one. For game two, we branch out, and we will have a game two. Like, there's no way to win a best of three series in one game. So for game two, there could be a win or a loss, and a win or a loss. So this shows all the ways that two games can be played. And let's put those probabilities there, 0.7, 0.3, 0.7, and 0.3. And you can, if you feel like you need to pause the video to just try to play catch up, like, you do what you need to do. So here is where we have to be very, very careful. So this is from the Dragons' perspective. If they win the first two games, then they've won the series. I'll put a red check mark there. They don't play any more games. Also, if they lose the first two games, they've lost the series. It's done. So for our final branch of our tree diagram in game three, we're only going to be branching off from these two guys, because these two guys, win-loss and loss-win, are the only two branches from game two where each team has won a game and will result in a game three. From there, we can win or lose, 0.7, 0.3, 0.7, 0.3. And if you want to, you can, that branch results in them winning, that one losing, this branch results in them winning, and this one losing. So with this question here, there are 6 possible ways the series can play out. They can win in 2 games, lose in 2 games, and there's 4 different ways to win in 3 games. Win, lose, win. So there's 4 different ways the series can go to 3 games. They can win by winning the first and third game, or the second and third game, or they can lose the series by winning the first and losing the last 2, or losing the first, winning, and then losing. This is all the possible outcomes. And they're not all equally likely. Let's look at the branches because we're interested. We've done part A. We're interested in figuring out the probability of them winning the series. So, which of these ending branches represent to win? There's three of them. So, first, what's the probability of the Dragons winning in the two games? Well, we have those probabilities based on our previous lesson. We know how to handle the probability of compound events. It's the probability of them winning game one, 0.7, times the probability of them winning game two, 0.7. So that's 0.49. There is a 49% chance that they'll just win outright in the first two games. There's two other ways they can win this series. Looking at the second possibility, win, lose, win. What's the probability of that happening? 0.7, 0.3 times 0.7. So we can do that. Again, you can pause if you need to. I'm going to do the math along with you guys. So that's 0.147 or 14.7%. And the third option is losing the first game and winning the last two. Lose, win, win. So that would be 0.3 times 0.7 times 0.7. Same numbers, different order. So we know that that will be 0.147 as well, or 14.7%. Later on, we might make these scenarios a bit more complex where the chance of winning or losing an individual game might change. But yeah, for now, this repeated calculation, you might have some repeated values, and that's okay. So we've now looked at, these are the three different ways they can win the series. So the probability that I might just say win, like for winning the series, is going to be 0.49 plus 0.147 plus another 0.147. If we do that, 0.49 plus 0.147, 0.784, or 78.4%. So let's think about this, everyone. Most of you, the majority, in the survey question online, thought that if the Raptors were only 70% likely to win a single game, that they'd be less likely to win a series where they play more than one game. But what actually is true is the opposite. If a team is 70% likely to win a single game, if they play more games, like a 3-game series, that actually increases their chance of winning and gives the team with the most skill, gives their skill a chance to kind of win out. So I thought you might find that interesting. The majority of you guys were incorrect in thinking the Raptors would have a lower chance. Now, of course, this is just a 3-game series. We'll look at later a 5-game, a best of 5 game series, and look at if it's more or less than 78.4%. We won't get into 7-game series, but the concepts we apply here will work for that as well. So that was a pretty straightforward scenario where each individual game was 70% chance for the Dragons to win. But we can, if we want to make it more realistic, we can do that. We have the capability. So let's do a second example. So we're going to tweak what we did a little bit. So this time we're going to try to add some realism. So let's say they're playing 3 games, but in like the NBA, NHL, baseball, the home team, the team that had the better record in the season, gets to play more games at home. So in this question, we're going to say the Dragons play the first and third game, like if they need to have a third game, at home. And they have the advantage at home. They're going to win. They win 80% of their games at home. We'll say they have an 80% chance of winning. And they play their second game on the road where they have a 50% chance of winning. So I just made these arbitrary numbers up. But like if you were a fan of the team or league, you could base these percentages on how they did against that team in the regular season, or whether a certain team has some injuries. You can tweak it however you want. Let's repeat what we did earlier. So it's another best of 3. And so our tree diagram will be the same structure as before. However, game 1 will be 80%, 20%. Game 2, which is for sure played, is going to be 50% chance of winning and 50% chance of losing. And then just like the previous one, if we have 2 wins or 2 losses, it's over. And so we only need the following in our last layer. And this is game 3 is at home. So the Dragons have a 80% chance of winning, a 20% chance of losing. So take a moment, let that digest. But yeah, games 1 and 3 at home, higher chance of winning. Game 2 on the road, less chance of winning, 50%. And so now we can analyze the probability of them winning the series, but looking at of the 6 possible ways the series can play out, there were 3 where they actually won. And so you guys can repeat the same calculations we did on the example 1. You can organize it like me or in your own way. So if you want to pause the video and try that, you can, or if you just want to follow along, you can do that too. So the 3 cases to win are winning the first 2 games, or winning, then losing, then winning, or losing, then winning, then winning. Chance of winning the first 2 games, 80% and 50%, so 0.8 times 0.5. Use some mental math there, that's 0.4. Win, loss, win. So win at home, 0.8. Losing on the road, 50%. Winning at home, 0.8. So we're using the probabilities for game 1, game 2, game 3 from our diagram, 0.8, 0.5, 0.8, the ones in our branches. That's why adding these in to your tree diagram can be very helpful. So 0.8 times 0.5 times 0.8, I believe that is 0.32. So 32%. So be careful here, because we've changed the probabilities between game 1 and game 2. You will not get you might not always get the same result. So here we're losing the first game. There's a 0.2 chance of that happening. And then winning game 2 on the road, 50%. Winning at home, 80%. So you can see it's a different calculation than when we just assumed it was the same chance of winning each game. So I got 0.08. And if we add up all those 3 cases, those are the 3 different ways that they can win this best of 3 series. 0.4 plus 0.32 plus 0.08 is 0.8, or they have an 80% chance of winning this particular playoff series. So another best of 3 example, just trying to add a bit of realism there. And really, you're only limited by your creativity with these kind of questions. You can add as many layers of complexity you want if you want to get a realistic chance of a team winning, or you can keep things as simple as you want. So let's do one more problem in this question. So much like in real life, a momentum does have a place in sports. Like in basketball, a player who's made 5 3-pointers in a row, the analytics of today's game actually factors this in, that a player is actually more likely to make their next 3-point attempt if they've made 5 in a row. I believe it's called the hot hand effect. But the same thing can happen with winning. So if you win a game, the momentum might indicate the chance of you winning the next game might increase. And if you win that game, it might increase again. So in this question, we're going to do this. We're going to say that they have a 70% chance of winning their first game. So we're still going to do a best of 3. But then we'll say if they win, their chance of winning the next game increases by 5%. If they lose, it decreases by 5%. So trying to add another layer of realism to this question. So our tree diagram It's another best of 3, so structurally it'll look the same. Game 1, Game 2, Game 3. Same combinations of wins and losses. So for Game 1, to start off, it's 70-30 again in this particular example. And so now we want to be careful. So for Game 2, if we're coming off a win, so we can win or lose, but for Game 2, if we're coming off a win, the setup of the question says our chance of winning will increase by 5%. So instead of a 70% chance of winning, because we won the previous game, we're going to have a 75% chance of winning, 0.75. That would make our chance of losing, not 0.3, our chance of losing, because these all have to add up to 1, right, would be 0.25. Going the other way for Game 2, if we lose Game 1, question says our chance of winning goes down by 5%. So our next game, our chance of winning would go down to 65%, which would make our chance of losing 35%. So after a win, add 5%. After a loss, we're taking off 5%. We know that there will be just 2 more branching off for Game 3. Can you use our rule? Just give it a try. These 2 win losses are coming off another loss. So if our current chance of winning in Game 2 is 75% and they lose, can you try to fill in the probabilities of winning Game 3? Same thing if their Game 2 chance of winning was 65% and they won, how would that affect the probabilities for Game 3? If you want to pause the video and try that, you can, or you can just follow along right now. So coming off a loss, their chance of winning decreases by 5%. So if it was 75%, now it's back down to 70-30. Their chance of winning Game 2 in this branch was 65%, and if they won, that's going to tick up by 5%, so it's back to 70-30 as well. So trying to add a little bit of realism. Again, you can play around with these as much as you want. Again, you're just limited by your own creativity. But now that we've done the tree diagram, we can find the probability of winning. We've done 2 examples already. You should try this one on your own. You can pause the video and unpause it when you're ready to check your answer. I'm going to go ahead and set it up like the previous 2 examples. And then in a moment, we'll look at a best of 5 example. So win-win. This is now easy to visualize with our tree diagram. 0.7 times 0.75. Win-loss-win is 0.7 times 0.25 times 0.7. Loss win-win is 0.3 times 0.65 times 0.7. I've kind of squeezed myself off to the edge here. That's okay. I'll squeeze these results in here. So 0.7 times 0.75. And there's really no real need to round any of these. These are nice and exact. So 0.525, 52.5%. 0.1225 for winning, then losing, then winning. And finally, 0.3 times 0.65 times 0.7. 0.1365. And to get our chance of winning the series, we take those cases and add them up. 525 plus 0.1225 plus 0.1365. Get that as a decimal. So 0.784 or 78.4%. So if we use these values in this scenario, 78.4%. All right, let's look at our final example. So I'm going to help you guys with this one. Instead of a 3-game series, what if it was a 5-game series? So we're going to revisit example one. So in example one, every game was a 70% chance of winning. So we're going to keep things simple for this one here. Um, so in this case, we're going to do a best of 5 series. So this adds a layer of complication. This means a team has to win 3 games. So once a team wins 3 games, it's over. So if the Dragons win 3 games, they stop playing, or if they lose, they stop playing. And so in this case, there'll be some options. They can win in 3 games, in 4 games, or in 5 games. So I'd like you to see if you can make a tree diagram for this one. Just give it a try. You can always unpause the video and just kind of follow along with me. I have given you a hint. If you made your tree diagram correctly, there will be 1 way that they can win in 3 games, 3 ways to win in 4, and 6 games to win in 5. So maybe give the video a pause and try that on your own. But here I go. We're going to do this one. I'm going to leave a lot of space between my 2 sides, win-loss here, just because this tree diagram is going to get pretty big. So 0.7, 0.3. And then I'll branch off like this, win-loss, trying to keep things spaced out. So in a best of 5, they're always going to play at least 3 games. So what you will find is that our tree diagram will kind of look like the 3 coin flip, because they're going to play 3 games no matter what. And then finally, win-loss, 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 win-loss. For this particular problem, because each win is 0.7 and each loss is 0.3, if you don't want to add in the values here, that's okay. If you do a problem where the probabilities change, maybe leaving them in is better. I'm just going to leave them in. So this is how the first 3 games could play out. All 3 games are played no matter what. But now we can see some branches will end. We can see that in this leftmost branch, the Dragons have won the series. They've won 3 games. They don't need to play anymore. And the same with on the right. They've lost 3 games. So they don't need to play anymore. So we're only going to keep branching out from the remaining 6. Try to be efficient with how I use my space and keep things, fairly spread out. Definitely understand that adding a lot of layers here can get clogged up. But I think we've done a good job here. It's not looking too bad. 3.7, 0.3, 0.7, 0.3, 0.7, 0.3. All right. This is for game 4. So you have to be careful now, and we got to think about which of these branches are going to end. So working left to right, you can see here we've won, lost, and 1. This results in a win for the Dragons. 2 wins and 2 losses means we're going to have to go to a 5th game. So I'll just do a little mini branch out like so. Win, loss, win, win. That's a win for the Dragons. Win, loss, win, loss. Going to need to branch out. Win, loss, loss, win. Going to need to branch out. And in this particular branch here, they've actually lost a series. Loss, loss, loss. That will stop. Moving to the right half of this diagram, loss, win, win, win. They've won 3 games. This branch is done. This branch needs to go further. Loss, win, win, loss is 2 wins, 2 losses. Same with the next one, loss, win. That's 2 wins, 2 losses. But now we have loss, win, loss, loss. This branch is done. The Dragons have lost the series. Loss, loss, win, win. That will need to branch off. And loss, loss, win, loss. that will end. So this is what our tree diagram would look like for the first 4 games. And we can see there is now one way that they can win in 3. They just have to win all 3. And you can see there's 3 ways they could win the series in 4 games. And again, we'll find those probabilities later, those individual ones. Let's finish this off. Win-loss, win-loss, win-loss. And I think just for the sake of managing space, I won't add in the 0.7, 0.3 for those last guys. You can assume that they're there. And so we don't need to worry about which branch. All these branches have ended now. You can't play more than 5 games, which result in a win for the Dragons. Any branch here ending in a win will mean they've won their 3rd game. And so we've got 6 different ways that the Dragons can win in 5 games. So what's left for us is we have to look at these individual branches. There are 10 of them. Find their individual probabilities and then add them up. Now, this particular problem isn't so bad because they're with the chance of winning and losing staying the same with a lot of repeated calculations. And so that's going to save us some time. So for 3 games, I might do my work over on the left. There's only one way that can happen. The probability of winning the first 3 games, it's 0.7 times 0.7 times 0.7, or 0.7 cubed if you want to make it more efficient. So 0.343. They have a 34.3% chance of winning. Let's look at the probabilities of them winning in 4 games. So the probability of winning, so the first option for game 4 of them winning was a win, a loss, and a win. So win, loss, win. That'd be 0.7 times 0.7 times 0.3 times 0.7. Can do that calculation. So that would be 0.7 times 0.7 times 0.21, 0.1029. And astute observers will recognize that because each of the options for winning in 4 games, the second option is to lose the second game, and the third option is to lose the first game and win the last 3. It's the same combinations of numbers, and it will be the same result. So we don't need to rewrite the math there. Lastly, let's look at 5 games. Might have to squeeze this in a little bit. So for 5 games, so the first way to win in 5 games, starting left to right, would be win, loss, win. So that'd be losing the 3rd and 4th games. Win, loss, win. I work below, so that's 0.7 times 0.7 times 0.3 times 0.3 times 0.7. Or 0.7 to the power of 3 times 0.3 squared. No real need to, let's keep things as accurate as possible. So 0.03087. And this is going to be the same as, so I might just put this down. It might be good just to write out all the remaining cases. So maybe you want to just pause the video, and for these final 5 cases where they've won the 5th game, what's the combinations of wins and losses, if you want to try that on your own, or you can kind of do it along with me here. So that second option working left to right was win, loss, win. That's also 0.03087. The third option is win, loss, win, equals, I'll just do a little double tick there to indicate it's the same value. And then with the right half of the diagram, that's losing the first game. It's lose, win, lose, win. same value. Second to last one is lose, win, lose, win, win. Same value. And the final one is losing the first two games and then winning the last. So that's what our tree diagram says, the 10 branches that lead to a win. We've summarized them all right there. The probabilities are a lot of repeated calculations, so we don't need to rewrite them in many cases. And all that's left for us to do is to find the total. The probability of a win is going to be 0.343. There were 3 ways to win in 4 games, and each one of those, I shouldn't put that squiggly line down as far, that's okay, was 0.1029. And there were 6 ways to win in 5 games, and each of those had a probability of 0.03087. So you guys try that out. So the interesting thing to ask is, are they going to have, because we saw that in 3 games, they had a 78.4% chance of winning in a best of 3. Does that increase if you play more games? Let's find out. 3 times 0.1029 plus 6 times 0.03087. 0.83692, or 83.692%. So the longer the series, the more likely it is that the better team is going to win. It gives them their skill more of a chance to kind of come out. So it's not impossible for an upset to happen, but this is why generally upsets are more rare in the playoff series than the regular season. It's because in these long games, the chance that the better team, just their chance of winning is increasing and increasing and increasing. And so for a best of 7, we won't do that. Obviously, if this is the diagram for a best of 5, a best of 7 diagram would be even bigger. So I hope you enjoyed that. I'm just going to quickly talk about